We've seen most of the method for simplifying the SEI growth model down to a volume averaged 0D algebraic approach, but one thing we still don't know how to do is to solve this equation, which is a critical step. We need to be able to find Js that satisfies both sides of this equation for some cell applied current I applied. Normally, when you're presented with, this is called an implicit calculation, by the way, as opposed to an explicit, because the solution variable is on both sides, and it's not at all clear how to perform any operations on this equation to get the variable on one side and only instead. One way of solving it would be to use iteration, and in fact, in the original paper by Randall and company, that's exactly what was done. Was we would guess a value for Js, and then you plug that value into the right-hand side, and you solve for the value on the left-hand side, and then you plug that value back into the right-hand side and solve for the left-hand side, and you do that a number of times, hopefully until it converges. Now, that's not guaranteed for a general nonlinear equation, but we found that it actually did converge all the time, and within about 10 iterations it worked quite well. However, it also turns out that we found out later that there is a closed form solution for Js, and I don't think this is at all obvious that is the case. To see this, let's take the equation that we're starting with and simplify notation by defining some constants. So Js of k is equal to this whole thing, which is just a constant. It's ugly looking. We'll call it A. Times exp times inverse hyperbolic sine of this whole thing, which is an ugly looking constant. We'll call it B. Plus this whole thing, which isn't quite so bad looking constant. We'll call it C times Js. So we end up with Jsk is A times exp inverse hyperbolic sine of B plus C times Js. Okay, it looks a little bit cleaner, but it certainly doesn't look solvable yet. One thing that we will note later on is that A is always negative and C is always positive, and that will be an important observation a little bit later, but not yet. Another important observation is that A, while it has some nonlinear operations in it, like exp and multiplications and divisions and whatnot, looks complicated. We can actually store it in a lookup table, and here I say a lookup table versus theta n. It's also possible to do it in a lookup table versus cell state of charge. So it's very easy to calculate in real time. You simply look it up based on cell state of charge. And the same would be true of C and of B, except you still would have to multiply by this I applied, which would be different in every time you're looking at it. So A, B, and C, pretty easy to compute from lookup tables, and then I'm left with this other functional form here, which is not so obvious how to solve for J. Until you come across a table of interesting mathematical identities and happen to notice this one. The exp of the inverse hyperbolic sine of x can be written in a, well, not quite polynomial form, I guess, but in a much more standard non-trigonometric kind of form. And that's what we're going to take advantage of. We're going to take advantage of that identity because, look, the structure is the same. exp a sine h of thing, exp a sine h of thing. So we're going to take advantage of that to solve for Js. So the first thing we do is write, well, Jsk, based on this, is, can I get it both? Not really. So it's A times this exp thing. So it's A times the right-hand side thing. And the right-hand side says x. Well, x was B plus Cj. So I have x there plus square root of x squared, so B plus Cj squared, all plus 1. There's my equation, which looks a little bit more manageable because we've gotten rid of the trig things. What I'm going to do is I'm going to isolate the radical on the right-hand side by bringing everything else over to the left-hand side. So I'll divide both sides by a, that gets rid of this. Then I'll subtract this from both sides, and that gives me this new left-hand side. Js over a minus b minus c times js equals the remaining square root. And I could work with that just as is. I chose to re-multiply through by a. I thought that was a little bit simpler if I did that, and then notice that I've got a js there and there that I can combine together. So I end up with js times 1 minus ca and minus ab on the left-hand side, and then a times this square root on the right-hand side. So the reason for isolating the radical on the right-hand side was that now I can square both sides of the equation and get rid of the radical. And squaring the left-hand side, I just wrote it as itself squared. And squaring the right-hand side, well, a squared, and then everything that had previously been underneath the radical. So b plus cj all squared, and then the 1 times a squared stays as a squared. Now it's just a matter of some algebra. And let's see if we can follow what happened here. So this is that, and this is that. And notice that this here is that, so I've just brought it all over to the right-hand side. And I'm multiplying out what this is, so b plus cj all squared gives me b plus 2bcj plus c squared j squared, and then I've got this a squared is there, and then this here, multiplying all of that out, I've got that thing all squared, so js squared 1 minus ca all squared, and then minus 2 times the product, so minus 2ab all times this js, 1 minus ca, and finally minus ab all squared, so plus a squared b squared. All of that works there. If I look at what's left, I have some js squared components, and so that's here. So what multiplies js? I got, it looks like an a squared c squared term. There that is. And a 1 minus ca squared term. There that is. And I've got some just plain JS terms. There's a plain JS term right there. So combining those, it looks like I've got an a squared times 2bc. So 2a squared bc is there. And down here I've got a minus thing, so I have plus 2ab 1 minus ca all times js. And finally I've got units terms, so an a squared b squared term, an a squared term, and a minus a squared b squared term right there. And it looks like this is going to cancel with that and leave an a squared. And this 1 minus ca squared is 1 minus 2ca plus a squared c squared. And that's being subtracted, so this is going to cancel that, and I'm left with only this 2ca minus 1 left over. And there's some cancellations here as well, I think. So I've got 2a squared bc and 2abc times ca canceling out. I'm left with only 2ab left over. Wow. Let's pause a moment. We've been tracking a bunch of algebra for a few lines. Let's remember what we're trying to do. We're trying to take the equation at the beginning of the previous page, which was this transcendental equation, implicit equation with js on both sides, and I was trying to solve for it. And we were able to reduce that transcendental implicit equation into this. A, B, and C are just numbers that I can look up in a table, we said, or compute. So what I'm left with is an equation for j that's quadratic in form. And we know how to solve quadratic equations. We've been doing it ever since high school. So how do I solve a quadratic? Well, j, if this is the little b term, this is the little a term, this is the little c term, is minus little b plus or minus little b squared minus 4 times little c all over 2 times little a. It's that right there. And if you look at it, there's some cancellations. There's a 2 and a 2, and inside the radical the 4. Those go away. The minus sign here can switch these terms around there. And that would just make this minus plus instead of plus minus, which is the same thing. I've got an a squared in here, which I can pull out to be an a out there. And we have a somewhat simpler calculation. It's telling me, though, that there are two possible solutions. It wasn't obvious from the implicit equation, but from this we see that Js can have two possible values. Which one to use? Well, the Routh test is something that we can use applied to this here to give us some guidance. And the Routh test, if you remember, is a geometric test which says for some polynomial, are the roots in the left half plane, are the roots in the right half plane, are the roots one in one plane and one in the other plane. It's used in control systems a lot, but we're going to use it here. And if you know about the Routh test, here's the Routh matrix that's formed. If you don't, then I wouldn't worry about it too much. But the Routh test says form this matrix using all the magic tricks of the procedure, and then look at this column. And I'm not going to tell you exactly where the roots of the polynomial are, but the number of roots that are in the right half plane is equal to the number of sign changes in that column. And this is why it was important earlier for us to say the signs of C and the signs of A. And it turns out that 2ca minus 1 is always less than 0. So this is minus. And a squared is always bigger than 0. 2 times a times b depends on b, and b is the applied current, so that it could either be positive or negative depending on the applied current. But the point is, if it's positive, I go from minus to positive, which is one sign change, to positive, which is no more, so there's a total of one sign change. Or if it's negative, I go from minus to minus, which is no sign changes, but minus to plus, which is one sign change. So it doesn't matter what b is. I have exactly one sign change in my Routh array, which means I have exactly one root in the positive right half plane. And by the fundamental theorem of algebra, I either have real roots or complex conjugate roots. So if I have one root, it has to be real. So I have one positive real root, and I've got one negative real root. Physically, we know that the side reaction flux has to be negative because A is less than 0. If you go back and look at the original equation, you would realize that there too. So that means that we need to take the smaller root. We don't want that one. We do want that one, the negative root of the equation. And because A is negative, the smaller root actually has the positive sign. So after all of this effort, what we've done is we've said if you define A and B and C as shown on the previous page, if you want to know what Js is, just solve this quadratic equation. Just punch the A, B, and C into this equation and you've got Js. So there's no iteration involved. We actually have a unique, explicit solution for the equation that gives us Js exactly, and that's actually pretty cool.